Okay, so linear algebra, this is about vectors, vector arithmetic, spans, and a little bit about linear independence. We'll see more of that in the next lecture. So what are vectors? Um, Vectors are roughly things that can be added together to get another thing of the same type, multiplied by real or complex numbers to get another thing of the same type. The same type stuff is what's called closure. We'll see a little bit more about that. Um, so a typographical note, usually vectors have a little arrow over them, but that's a pain to do in Word, so I'll write my vectors as bold. So what's a vector? Well, a functions, right? Can you add functions together, add and subtract them, and get another function? Yes. Heck. Can you multiply functions by constants? So if f of x is a function, is a constant times f of x a function? Yes. And all the usual rules for addition and subtraction and stuff apply. So functions, as long as we're careful about domains, you can think of functions as being vectors. And this is important to us because we want to be able to think of solutions to differential equations in a linear algebra sense, which means thinking about functions, the solutions, as being vectors. So the classic column vectors of R2 and R3. So A and B, right? This is my X component, my Y component. Can I add these kinds of things? They're just lists of two vectors. This is supposed to be C. That's A plus C, B plus D, right? You just add the corresponding components together so you can add those things. If we're in R3, that means we have three components, usually thought of as X, Y, and Z. If we multiply this by a constant, what do we get? Usually, well, always, we just distribute the constant to each term. So the k times A, k times B, k times C. So the usual classic column vectors, you can add them, you can subtract them, you can multiply them by constants. These are column vectors. And we can extend that to n. So B1, B2, dot, 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 Bn, like you have 17 column vectors. You can add, you can subtract, and you can multiply by constants. And keep in mind that our constants are almost always going to be just real numbers. So real numbers and complex numbers. So this kind of weird R here, that stands for real numbers. This weird C thing stands for complex numbers. So if we take two real numbers, say A, and here I'm going to put a little arrow on top of them, and B, can you add them together? Yeah, you just add the numbers and you say, well, that's a vector. It becomes a little bit weird and the notation becomes strange if I'm thinking about multiplication, because I'm going to think about one real number as a vector and then I multiply it by a constant. And you can do that. So this would be 3 plus 7 equals 10, right? And 7 times 3, if think of 3 as a vector, that gives me the vector 21. It's a little weird, the real numbers by themselves being a vector space, but as we'll see later, that actually becomes very useful in dealing with solutions to differential equations. Complex numbers we're not going to do a whole lot with, but we will mention that going through. Now, here's some things that are not vectors. The integers are not vectors. You can add and subtract them. Right? 5 plus 7, for example, is equal to 12. Integer plus integer gives me an integer, but pi times 3, right? Here's my integer. Here's a real number. This is not an integer. It fails closure, right? And one of the important things about vectors is when you add two vectors, you get another vector. But if we just look at the set of integers, if I multiply that by a real number like pi times 3, that's not an integer, right? So we don't have closure. And we want constants times vectors to be vectors. Graphs in the graph theory sense are not vectors. So a graph, in a graph theory sense, you have a bunch of vertices and a bunch of lines, segments, edges connecting them, right? So there's two graphs. These are my vertices. We'll make them fairly large dots. And the problem is that it's really hard to define addition, right? What does it mean to add two graphs? And so we don't actually have a nice sense of addition there, so it can't be vectors. So vectors, our basic ideas is the functions or the column vectors, and those are and we can multiply them by real numbers. So a formal definition of vectors, this is a definition of vector space. We're not going to do a whole lot of this, but this is the formal definition. Basically, what's a vector? A vector is something that's in a vector space. And what's a vector space? Well, it's a collection of things with a collection of numbers. Usually the real numbers are scalars, so that should be underlined. And then obey these rules. These are our closure axioms that we mentioned above, right? If you add two vectors together, you get another vector. If you multiply a vector by a scalar, you get another vector. And then a lot of this is just sort of the usual things you expect addition to do. Commutativity, associativity, there's a zero thing, the zero vector plus v1 is v1. And given a vector, there's an inverse one, we call it minus v, so that v plus minus v equals 0. This is the negative of v. We can multiply by scalars. The number 0 times a vector gives you the vector 0. The number 1 times a vector just gives you back that vector. Minus 1 times v, that gives you the additive inverse. Right? So everything that you know about addition and multiplication pretty much follows through. You can multiply by scalars in whatever order you want, and you have distributive axioms that multiplication distributes over addition, like usual, and c plus d, two scalars multiplied by a vector, you can distribute the vector. So it's the usual kind of distribution thing. Keep in mind that these go both ways, right? It goes this way and that way. Could have just as easily written this as cv1 plus cv2 is equal to cv1 plus v2, right? Equations convert from one side to the other. It doesn't really matter which one you start with, although we tend to start with the left side. So Rn, how does vector addition and subtraction work in Rn? So v1 plus v2, put little arrows over there for now. Just add the components. 2 plus minus 5 is minus 3. Minus 1 plus minus 2 is minus 3. 3 plus 6 is 9. And likewise, you can subtract just by subtracting the components. 2 minus minus 5 is 7. Minus 1 minus minus 2 is 1. 3 minus 6 is minus 3. Right? So we just subtract the components. Remember, each one of these entries those are the components of the vector. So when we're adding them geometrically, so arithmetically, you just add the components. Geometrically, there's a nice thing called the vector parallelogram. So if we have W1 and W2, we can draw these in the plane. This is my X component is 1, my Y component is 2. So we go to X equals 1, Y equals to 2. Then we draw an arrow that starts at the origin and goes up to that. So there's my vector W1. W2 is minus 2 is my X component, and plus 2 is my Y component. So it'll end there. And we just draw in that vector. Wow, that was kind of a weird arrow, but I'll take it. So this is my vector W1. This is my vector W2. So if we add them, what do we get? Well, we can do this component-wise, like we just did. That becomes minus 1, 4. So minus 1, 4. We should get a vector I'm just going to put this in sort of dashed. That goes up here, maybe a light line. So that would be the addition. One way to think about the addition is that we're going to take W1, and that tells me to go 1 unit in the x direction and 2 units in the y direction. And then I'm going to do W2. And what does W2 tell me to do? It tells me to go 2 units in the negative x direction. That would take me over here, and then 2 units up. So that ends up there. So if I put W2 with its tail at the tip of W1, right, and just travel this triangle, I get W1 plus W2, which is the diagonal of that. Likewise, W2 says go -2 in the x direction, 2 in the y direction, you end up there. And then W1 says go 1 in the x direction and 2 in the y direction, so you go up there. So we do W2 first and then W1, we end up there. And so we end up with a nice parallelogram, right? W1, just translate up there to the end of W2, and that gives you W2 plus W1 or W1 plus W2, and the long diagonal here is W1 plus W2. So that goes there. Now W1 minus W2, V1 minus minus 2, that equals 3, and 2 minus 2, that equals 0. So it's tempting to just draw W1 minus W2 as this vector, but we want to relate it to W1 and W2 themselves. And so this vector plus W2 should give me W1, right? So if I start with W2 and I go up here, then how do I get to the tip of W1? Well, I go 3 units to the right. And so that's W1 minus W2. So right, so if we do W2 first and then 3, 0, we end up at W1. So that's how we can add and subtract things geometrically. We get this nice parallelogram. One of the diagonals is the addition. The other diagonal is the subtraction. Right, so V1 and V2 are now, let's see the example 9. V1 and V2, this is very hard to do. So V1 is 2 minus 1, 3. I'm just going to copy this and bring it down here. And I'll have to bring this up a little bit so I don't screw up all my spacing. Okay, so that's that. That's a little bit hard to draw because in 3 dimensions you have to think, okay, so here's my x coordinate, here's my y coordinate, here's my z coordinate, except I think my picture does the other method. So this is x here and this is y. So this is 2 units in the x direction, 1, 2, and then minus 1 unit in the y direction, and then 3 units in the z direction, 1, 2. So there's V1. V2 is minus 5 in the x direction. So this is my x. So that'll be over here somewhere, minus 5, minus 2 in the y direction, and 6 in the z direction. So it looks like that. So drawing things in 3 dimensions is hard. Drawing things in 10 dimensions is just sort of out the window. But you can ask GeoGebra has a 3-dimensional calculator. And if you ask it to do this, it can. So V1 plus V2, this is my V1 here, and this is my V2. Adding them together is the red, right? Because this is V1, so V2 plus V1, that gets me this long red vector. And the green vector that points from V2 to V1 is pointing from V2 to V1. Is V2 minus V1? V1 minus V2. Let's get that kind of backwards. Right, because if I add V2 to this, I had this black vector and this green vector, I get V1. So this is, again, a parallelogram. And all of those vectors, all 6 of them, lie in one plane, this blue shaded thing. And so that gives me a sense of how addition works also in 3 dimensions, right? It's a plane, 2 vectors define a plane, and then in that plane you get this parallelogram. Okay, scalar multiplication in Rn. Here we just multiply all the components by the same vector, so 2 times V1 is 2 minus 1, 3. 2 times 2 is 4. 2 times minus 1 is minus 2. 2 times 3 is 6. Minus 3 halves times V2, where V2 is minus 5 minus 2, 6. Minus 3 halves times 5 is 15 halves. Minus 3 halves times minus 2 is 3. Minus 3 halves times 6 is 9. Minus 9. Right, so we just take this, we distribute it to all 3, and we get the multiplication. Geometrically, this is just sort of extending and contracting or possibly flipping a vector. So if we think about W1 now as having been, oh, what did I write down W1? Oh, W1 was back up here. I apologize for this. Is 1, 2. Drawing an x-axis and a y-axis, x, y, 1, 1, 2. So there's W1. So 2W1 is 2, 4. So 2, 3, 4. So that'll be up there. And note that this line defined by this vector has a slope 2 divided by 1, right? Rise of 2, run of 1. So this point also, 4 and over 2, that's a slope of 2, right? So this is a slope 2. 2W1 points in the same direction. It's just twice as long. Pi W1 would point in the same direction, but just be pi times as long. Now, minus 1/2 W1 is minus 1/2 minus 1. So we take our minus 1/2, we multiply by each component. What direction is that? That's minus 1/2 would be about here, and then minus 1 would be about there. And that's also on the same line, right? So all multiples of a vector, the single vector, lie on the same line that the vector is defined by. So geometrically, we can look at these kinds of vectors and do some kind of a geometric understanding of what multiplying by a scalar means and what adding 2 vectors means. So what about functions? This is just what you're absolutely used to in the past. Suppose we have 2 functions, f of x and g of x. Well, what's f of x plus or minus g of x? That's t squared plus t is f of x plus g of x. F of x minus g of x is t squared minus t. And 14 times f of x is just 14t squared. And this is just nothing new. It's just how you add, subtract, and multiply functions. There is no good geometric equivalent of that. And when we think about functions as vectors, we're only thinking about adding and scalar multiplying, right? Functions can be multiplied by each other. They can be composed with each other. There are lots of neat things you can do with functions, but that's not really relevant to their properties as vectors. Okay, so parametric lines and direction vectors. So what is this line? 2t minus 1, y equals 8t minus 7. This is what's called a parametric line, parametric presentation of a line. And so for each t, we get an x coordinate and a y coordinate. And this is generally why we use t and y in the differential equations part. We're going to be using x here to be the x coordinate. So we can plot this as the usual thing, right? Take -2, -1, 0, 1, 2. What points do we have? If t is -2, and we plug that in for x, you get -4, -1, that's -5. If t is -1, plug that in, you get -3. If you plug in 0, you get -1. Now, slope is 2, so we're just increasing by 2 each time. This becomes 1, this becomes 3. What about y? If you plug in t equals -2 in for y, you get -16 -7, which is -23. Slope is 8, so we're going to increase by 8 each time. So this would be -15, -7, 1, and then 8. 16 minus 7 is 9. So these are, we think of this as being position in the plane, and this is being time. So -523 is going to be way, 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 way down here, more or less. So this is -523. And we'll put a little label on that, t equals -2. I think just to make this a little bit easier, I'm going to shrink down a little bit so I can see much more of the picture. So t equals -2 is down there. At t equals -1, we're at -3, 15. -3 is about here. -15 is about here. So that's t equals -1. When t equals 0, we're -1, -7, which is about here. T equals 0. And then when t equals 1, we're at the point 1, 1. That's up here. T equals 1. And then finally at t equals 2, we're at the point 3, 9. About up here. Great. So what's the line look like? Well, we just connect all our dots. And it runs through this whole thing. So there's our graph. And we can write this in y equals mx plus b form, right? The usual slope-intercept form that you're used to. X equals this, y equals that. You can solve this for t. X plus 1 over 2 equals t. And then plug it into y. So y equals 4x minus 3. Our slope here is 3. Our slope here is 4. Y-intercept is 3 minus 3. I didn't do a good job of drawing it because we want to actually go through that point, but that's actually in there. So that's the y equals 4x minus 3. And that gives you the equation of this line without the t in it. So what's the importance of the t? Why is the t important? Well, the t, I think of, this should be a -1. I think of the t and the points on the line as the t is a schedule. And you're riding a train and it runs along a schedule. And these things are stations, right? At t equals -2, your train is here, and your train goes up this way. And at t equals -1, your train is there. And at t equals 0, your train is at this stop, and it keeps going. So the parametric equations are telling you where the train is along the track. This equation is just telling you where the track is, right? If you've ever lived near train tracks, you know the difference between having the tracks without a train and having tracks with a train. So Parametric equations, we'll see a bunch of these things. Sometimes you can get a nice equation for the train tracks. Sometimes you just have to plot the parametric equations as they are. But for lines, it's actually quite nice because you can always switch back and forth. We can write this in vector form. So what we'll do is we'll say two components, an x component and a y component for y. Our x is 2t minus 1, our y is 8t minus 7. Now we're going to use some of the properties of vectors, but sort of backwards. When we're looking at the equations for distribution and associativity and all the things, it's usually about taking things and putting them together to get one thing. Here we're going to break these apart. So I've got this column and this column, so I can break that into 2t, 8t, minus 1 over 7. Actually, we'll make it a plus and put all the minus signs in there so that we keep this. And I can factor the t out of this because the t is common to both of those things. So I get t times 2, 8 plus minus 1 minus 7. So that's a way to write a vector, right? Write this parametric, that's a way to write a parametric line, right, as time times a direction vector times what I call an offset vector. It doesn't actually have a formal name. So what does this mean about W? Well, 2 comma 8, put it like this, and minus 1 comma minus 7, minus 1, minus 7, somewhere down here. There's minus 1, minus 7. So this is my offset vector, B. So if I take a particular t value, say t equals 1, what does that tell me to do? It tells me go out to the end of this vector, minus 1, 7, and then do one of these, a 2, 8. So there's my t equals 1. One of these and then out there. If t equals 2, what do? I go down to the end of the offset vector, and then I go 2 units parallel to the direction vector. If I want t equals to 3, what do? I go down to the offset vector, and then I go 3 units this direction. If t equals 0, what do? Well, then this term is just 0, and so I just go down to the offset vector. If t equals minus 1, what do? I go down the offset vector, and then down, whoa, that's weird. I go down to the offset vector, and then I go 1 unit in the negative direction vector sense. So when we come back and look at this vector from here to here, that's my vector B. And the direction vector is this vector. This line here is parallel to this vector, but it's been offset away from the origin by this amount. So t equals 0, we're at the offset vector. T equals 1, we go down to the offset vector and up 1 unit in the direction of the direction vector. T equals 2, down 1 unit, and then up 2, etc., etc. So we can write lines in this form. This is your direction vector. This is what's called the offset vector. Now, this is really useful because suppose we have this equation, which we've seen before. This is a nice little differential equation. And we can solve this. Example 15. Oh, Lord, except I didn't actually write up the solution for it. That's kind of dumb. So I'll do this with undetermined coefficients. You can do it with integrating factors as well. So the homogeneous solution is the solution of this part equal to 0, and that gives you k equals minus 4t. My guess then becomes mt plus b because it's 16t, and the derivative is m. So putting these together to get my coefficients, what do I get? I get m plus 4 times mt plus 4b equals 16t. So my 4m has to be equal to 16, which means that m equals 4. And then m has to be m plus 4b equals 0, which means that since m is 4, that equals minus 4b, and b equals minus 1. So my general solution is k e to the minus 4t plus 4t minus 1, right? Homogeneous solution, particular solution. So if we think of these as vectors, functions as vectors, right? That's the offset vector, and that's the direction vector. So the solution to these first order linear equations are actually lines, formally. They're like lines, right? There's a direction vector, that's the homogeneous solution, and there's an offset vector, that's the particular solution. And so in function space, which is this big, weird, infinite dimensional thing, you pick out a vector, 4t minus 1, and then you go in the direction e to the minus 4t as far as it can go, and that gives you a line of functions in a function space. The point is that the structure of solutions for linear differential equations is that of a vector space. We can think of, when we're solving differential equations, we can think of them as being vectors, and we get a nice one-dimensional vector space here. The k is telling you how far you can go in each direction. So what's a span of a vector? So if you have a single vector v, the line t times v is called the span of it. So if v is 1, 2, there's my vector v. What's the span of v? Well, the span of v is all multiples of v when you multiply by any real number. So we would also, if t is 2, you would go up to 2, 4. So that point is in the span of v. And if you had t equal to 1.5, then you would be 1.5 and 3. That point would be on it. And if t equals 10, you would have the point 10, 20. Right? And actually, we're thinking of these as all being vectors. So that vector, but they all lie on the same line. And no matter what t you pick, you always get another point on that line. And if you start taking negative t's, you get all of these points down here. So the curve that's just t times v without any, just a direction vector, no offset vector, that's called a span, right? So there's the span of v. Is 3, 1 in the span? Well, 3, 1 is over here. That's not in the span, right? The span is this line. This vector does not lie on that line, so no. What about minus 2, minus 4? Yeah, if I drew it better, minus 2, minus 4, that should be on the line. Because it's a real number times this vector. So the span of an individual vector is just a line, and geometrically, if you can draw it, it's easy to tell whether or not a vector is in the span because is it on the line or not. What about this function of equals t squared, right? So from function space, is pi times t squared in the span of v? Yes, pi times t squared is a real number times v equals to t squared. So it's in the span, right? That's what it means to be a span for functions. Is t cubed in the span of v? So there, for the second question, we want to ask ourselves, is t cubed equal to a constant times t squared? It's our vector, scalar, so is t cubed a scalar multiple of t squared? And the answer is no. You can just graph the two functions. You can't take a parabola and multiply it by a constant. That just sort of tightens it or widens it, and get t cubed. So with functions, it's a little bit harder because you don't have the graphing ability that you have in V2 to tell if two vectors in the span. So if we look at two vectors, V1 and V2, what's the span of that? Well, it's all vectors of this form, K1, V1, K2, V2. K1 and K2 are parameters, and they're allowed to vary between minus infinity, and they're independent of each other. So you can pick any pair of numbers and plug them in. So what's 1, 3 and minus 1, 1? What's the span of those two? So here's 1, 3. It's this vector. And here's minus 1, 1. That's this vector. So what's the span of that? We'll call this V1. We'll call this V2. Well, we can take V1. We know that the span of V1 itself is that line. And this corresponds to, we go back up here, setting K2 equal to 0. Right? We set K2 equal to 0 and we let K1 just vary from minus infinity to infinity. We get the span of V1. That's just this line. What happens if we set K2 equal to 1? Well, that essentially makes V2 the offset vector. And so, let's see, 1, 3, so we'll go up here. So if we set K2 equals 1, we get a line parallel to the span of V1. Okay, what happens if we say, oh, this is supposed to be K2. What happens if we had K2 equal to 1/2? Well, that means we go halfway out here. Now that's our new offset vector, and we get another line like this. And in fact, if we let K2 vary, right, the span of V2 is all of this. So if you pick a K2, that means going out some distance on this vector, and then picking a K1 means going some distance parallel to V1. And so that means you can actually get to any point in the plane, right? If you pick a point like this, I can go a certain distance out along V2, and then I can go parallel to V1 and end up there. So the span of V1 and V2 is the entire XY plane, right? And so that's a nice geometric argument. Can you show this, that every vector in R2 is in the span of V1, V2? So let's take as an example here. I'm just going to pick some numbers. So suppose we take a vector W equals 4, 2. Right? And so that's 4, 2 is this point here. So we're looking at this vector. And so can I get to this vector by going along V2 and then parallel to V1. And yeah, it looks like I should be able to go in the negative direction of V2 down to about here, and then out to about there. So this would be my K2 is telling me how far to go this way. My K1 is telling me how far to go this way. And I want to know, what is my K1 and my K2? Well, that's actually not too bad. We just pull everything together. That, right? K1 times 1. We can bring the K1 into these and the K2 into there. And then we can add two vectors by adding the components, and we get this. And so what do we need to be true there is that 4 has to be K1 minus K2, and 2 has to be 3K1 plus K2. So how do we solve this? We use something called reduction, which means I want to add these two together, and that'll eliminate my K2s. So I get 6 equals 4K1. So K1 equals 3 halves. So what's K2 equal to? Well, we know 4 equals K1 minus K2. So 4 is 3 halves minus K2. K2 equals 3 halves minus 4. 1.5 minus 4 is minus 2.5. I think. So we go minus 2.5 in this direction. So we take V2, multiply it by minus 2.5, we end up there. We set K1 equal to, what's K1 equal to? 3 halves. We go this far in that direction, and we end up at 4.2. So we can think of these constants, these parameters, as how far do we go along one vector, and then how far do I go along parallel to the other vector. So we can actually show that that's true. If we did any vector, that would mean replacing the 4 and the 2 by an A and a B, right? And this becomes an A and a B, an A and a B. And then this becomes an A and a B, so that this becomes A plus B. And you can solve for K1. And once you know K1, you can solve for K2. So no matter what two components you choose, right, anywhere in the plane, you can always find a K1 and K2. So not every vector in R2 is in the span of V1 and V2, though. So if I take these two vectors, this is 1, 2, 1, 2, that points in this direction. And this vector is minus 1, minus 2, that points in that direction. Now, the problem here is that these two lines lie in the same plane. Sorry, that was just badly stated. These two vectors lie in the same line, right? So the span of V1 is this line, but that's also the span of V2, because V2 is in fact a constant, minus 1 times V1. So the span is the same, and so you can't get off that line everywhere. So a vector like 0, 2, for example, is not in the span of these two vectors because there's a degeneracy there. They're actually sort of picking out the same direction. So arithmetically, what's a vector that's not in the span? Well, we have K1, B, oops. Our span equation is this, plus K2, B2. And in this case, this becomes K1 minus K2 times V1. Because V2 is in fact just minus V1. So if I plug that in for the V2, then it becomes this. So any vector that is not a multiple of 1, 2 is not in the span. So pick a vector where the ratio of the x-coordinate to the y-coordinate is not 1/2. So if we take, say, 7, 7, that's not in the span of this. Question mark over that. Is there some t that gets me 7, 7 to be t times 1/2? So if I'm thinking about the vector 7, 7, is it possible that I can write it in that form? But that requires t equal to 7 and 2t equal to 7 to be true at the same time, and that is a contradiction. The usual symbol for contradiction is two arrows bonking into each other. So 7, 7, 0, 2, lots of vectors are not in the span. So that's a little bit of a warning, right? Two vectors often span an entire plane, but they don't have to because they might pick out the same direction. So vectors pick out a direction, is sort of the important point about spans. So in R3, can you draw the span of that? Well, I really don't want to, but it looks like this. So here's my two vectors, 0, 1, 2, 1, 2, 0. So this is V1 here, and this is V2. So what's the span of that? Well, it's you go along one vector for a while, and then you go parallel to it and end up somewhere, right? So the span means going in one direction and then going parallel to that. So if I go out a certain direction here and just run through all the points parallel to this, I get a whole bunch of stuff here and here. And in fact, this entire plane in 2 dimensions is the span of V2 and V1, right? So you picked out 2 of the 3 dimensions in space, and now you've got a plane floating out there. So what's a vector that's not in that span, say, 2 units in the x direction, right? That's not in the span. All right, so not every vector is in the span. Oh, that's supposed to be in R3. So this picked out 2 directions in 3 dimensions, 3-dimensional space, and that just gives you a plane. Here are 2 vectors picked out 2 directions in a 2-dimensional space, so that was everything. Here are 2 vectors only picked out 1 direction in a 2-dimensional space, and so we just got a line. So what's a vector that's not in the span? How do you do that? So here's our vectors. We want to find a vector ABC so that there are no solutions to the equation ABC equals K1 times V1 plus K2 times 0, 1, 2. And we can pull this together as saying A is equal to K1 plus K1. B should be equal to 2K1, Y component, plus K2. And C should be equal to 0K1 plus 2K2. So we've got 2 variables, K1 and K2, and we have 3 conditions. And so is it possible to pick A, B, and C so that not all 3 conditions hold? And that's, pretty easy. We can just say, let's set A equal to 0. We're allowed to pick these because we're looking for a vector that has no solution. So if we take A equal to 0, that forces K1 equal to 0. And then that makes B equal to K2 and C equal to 2K2. If we take C equal to 0, that makes K2 equal to 0. But then we can make b equal to 1. Zero, 1, 0 has no solutions, right? Because we're allowed to choose these. And if we choose this is 0, this is 1, and this is 0, then we get a contradiction here. So 0, 1, 0, in this case, is actually this vector along the x-axis, along the y-axis, and that's not in the span. It doesn't line that plane. So dealing with spans means solving a lot of equations. And of course, span of two vectors, this one. So our characteristic equation is that this is r plus 3 times r minus 2 equals 0. So r equals minus 3, r equals 2 are our solutions. And so the solution to this is k1 e to the minus 3t plus k2 e to the 2t. We think of those two functions as vectors. And so this spans a plane now in function space. It picks out all the solutions to this differential equation because various initial conditions will give you different values of k1 and k2. So it's the span of those two vectors. What's a function that's not in that span? Well, e to the t. So how do you go about showing that this is not a linear combination? Well, it's called a linear combination, but this is not, there's no k1 and k2 that give you e to the t. Well, we can divide both sides by e to the t. And we get that this, we want to pick k1 and k2 so that this thing on the right-hand side is in fact a constant and not just a constant, but the constant 1. And this can't happen because this right-hand side is never constant for choices of k1 and k2, unless you take k1 and k2 to be equal to 0, but then the right-hand side would be 0 and not 1. So there's a function that's not in the span. E to the t is not in the plane defined by those solutions. And big surprise, e to the t not being in the span means that e to the t is not a solution to this differential equation. Any function that's not in the span of e to the minus 3t and e to the 2t is not a solution. So linear algebra gives us a nice way to talk about solutions to differential equations. So the span of n vectors is just go down one direction plus another direction plus another direction, we allow it to vary from minus infinity to infinity. The span of a single vector in Rn is a line, unless your vector is 0, because then you just get a point. If you get two vectors, it's generally a plane, unless they point in the same direction, and then that's just a line. So this is going to lead us to the ideas of linear independence, dimension, and basis, but that's a talk for next week.